Today we're going to be proving the arc of hyperbolic cosine is equal to the natural log of x plus the square root of x minus 1. To begin, we know the definition of the hyperbolic cosine of x to be equal to, by definition, e to the x plus e to the negative x divided by 2. We're going to set this quantity to be equal to a. We can find the variable of x to be equal to the arc of hyperbolic cosine of a. This will give us the value of x by definition. Furthermore, we can find e to the x plus e to the negative x to be equal to 2a by multiplying 2 on both sides of this equation right here. Then we can assume e to the x to be equal to the variable of n. We apply this to get n plus 1 over n is equal to 2a. Combine n plus 1 over n to get n squared plus 1 divided by n is equal to 2a. Multiply n on both sides to get n squared plus 1 is equal to 2an. Subtract 2a on both sides to get n squared minus 2an plus 1 is equal to 0. We notice how n squared minus 2an plus 1 is written in the form of a quadratic equation stating ax squared plus bx plus c is equal to 0. This is the format of the quadratic equation, with the quadratic formula being the equation to solve the variable of x to be equal to negative v plus minus the square root of b squared minus 40c divided by 2a. We're going to apply the quadratic equation into n squared minus 2an plus 1 is equal to 0, a quadratic equation, to find the variable of n's value. And within this quadratic equation, the a quantity will be equal to 1, b quantity being equal to negative 2a, the c quantity being equal to 1. We can apply this accordingly into our quadratic formula. Negative b being equal to 2a plus minus the square root of b squared, 4a squared, minus 4 times 1 times 1, which is equal to 4, divided by 2 times 1, which is also 2, which can be equal to 2a plus minus 2 times the square root of a squared minus 1 divided by 2. I have not changed anything because all I simply did was factor out the square root of 4 from the square root of 4a squared minus 4 right here. I factored out the square root of 4 from this square root. We can divide 2 from the denominator into the numerator to get a plus minus the square root of a squared minus 1 being equal to the variable of n being equal to e to the x. Remember our previous assumption to let e to the x be equal to the variable of n's quantity. Hence, we can apply back e to the x into our variable of n. We can find the variable of x from here to be equal to the natural log of a plus minus the square root of a squared minus 1. But we are not done yet. We must argue whether we take the plus sign or the negative sign or both. To argue this, we must first analyze e to the x's range. What is the result of e to the x going to be within? Well, e to the x power, the result of this will always be greater than 0. X can be equal to all real numbers, that being negative, let me rewrite this, x being within like negative 3, negative 2, negative 1. So any negative number, x could be equal to 0. X could also be all the positive even integers such as 1, 2, 3, 4, or even decimals such as 3.65, 4.1, or even natural numbers such as e to the x or e to the e or e to the pi. They will all work. And the reason why for this is because, well, we all know that positive integers substituted into the power of x, such as e to the third and e to the second, will result in quantities greater than 0. That is all common sense. But what about negative numbers, such as e to the negative first power? Well, e to the negative first power will be equal to 1 over e, which will be still greater than 0 because the quantity of e is not equal to infinity. Only when e is equal to infinity can 1 over e be equal to 0, which we know e will never be equal to infinity. Hence, e to any negative quantity will always remains to be greater than 0. Hence, with one of the proofs and arguments out of the way, we must analyze this square root right here. For what range of a? For what range of a will this be true? Well, we know that within the square root for real solutions, whatever a quantity within, such as a1, a's of 1, no matter what quantity that is, like 1 plus 3, 1 minus 3, this resulting quantity, this a quantity, has to be greater than 0. And the reason why, because we cannot take the square root of negative 3. That would be a complex number, such as 3, the square root of 3 times I. And we're not looking for complex solutions. We're looking for all the real solutions. Therefore, A's range has to be less than equal to, or not less than equal to, greater than equal to 1. And the reason why for this is because we cannot substitute 0, because if we have 0, this would become the square root of negative 1. We cannot have the square root of negative values. And if we have any negative integer for a, such as negative 3 plus minus the square root of 8. You might realize, well look, the square root quantity inside is greater than 0, so this should work. But notice our previous argument that e to the x, the resulting quantity of e to the x, must always be greater than 0. And negative 3 plus or minus the square root of 8 will always result in a negative quantity. Hence, we cannot take values that are less than 0 or equal to 0. We can only take quantities that are greater than or equal to the positive integer of 1. Hence, x to be equal to the natural log of a plus the square root of a squared minus 1. Not minus. And remember how we've showed that we can find the variable of x through the arc of hyperbolic cosine of a. That x is the same x as this x. So we can substitute that to get the arc of hyperbolic cosine of a is equal to the natural log of a plus the square root of a squared minus 1. The exact same formula that we were meant to prove right here. Hence proving this identity for the arc of the hyperbolic of cosine x to be equal to the natural log of x plus the square root of x minus 1.